Hi, good morning everybody. My name's Adam Mactavish from Currie Brown, and I'm going to talk a little bit about some work that Currie Brown together with AECOM have been doing for the Committee on Climate Change, which Lynn alluded to at the end of her presentation, and talk through some of the elements that we investigated and what that's drawn us to conclude about the next steps for building standards in the UK. So the aim of the research was to look at whether there was potential to tighten and change building standards for energy and climate mitigation in particular, and if so, what were the sorts of standards and what might be the form that should take. I should say it was supposed to be a quick 3-month study, and we're now entering month 13, which gives you a feel for sort of the number of different paths that we've been up and down over that period. We should be producing the report that provides further detail on the findings that were published by the committee last week or the week before, and that will give a lot more granular detail supporting, in terms of the evidence base supporting their conclusions. So I thought I'd start off by cutting to the conclusion rather than taking you on a long journey to get there. And I think it's really positive and quite exciting from my perspective, having been involved in various initiatives with Lynn and others over the years where we've looked at opportunities to reduce carbon, and we've always come into a situation where we found it difficult to justify some of the investment in energy efficiency on the basis of cost and cost effectiveness from a public policy perspective. I think that situation has changed quite dramatically, and we're now in a position where for a range of factors, including the decarbonisation of the grid and changes in cost, evolving construction methods, that we can be looking at achieving a plus 90% reduction in the lifetime operational carbon emissions of a home for what is actually a very small capital cost increase, certainly one that's outweighed by the savings over the life of that property, delivering annual savings to households, a much more comfortable, high-quality living environment with better air quality, better sound insulation, and better thermal comfort. So really at the cusp of quite a great opportunity to make a real change in the buildings, in the new building stock. Of course, there's always a but, and in this case, the but really relates to the fact, although these are all proven technologies, and they're the sorts of technologies, they're probably half a dozen examples of all of them in this room today. If we're talking about building 300,000 homes a year, which is the ambition by the mid-2020s, doing that and changing the technologies we use to heat those homes across the board, and the way in which they're built, the sorts of technologies and methods we use for construction, although they're established, they're not mainstream. So that transition of managing that so it's done without causing too many risks to the performance of homes, too much disruption to the industry, is a key challenge. We did some analysis on the impact of delaying action and what happens if you were to build to current standards and then try and retrofit to higher standards in the future. What that showed us was both the costs were 7+ times higher if you try and achieve the same standards via retrofit. So the new build is your big opportunity, and we really don't want to miss that opportunity. And also, the carbon penalty that you pay is really quite substantial, and I'll come on to the analysis around that. So every year that you delay retrofitting to these higher standards, you're incurring quite a big carbon penalty, which is significant even over the 60-year life of that home. And I suppose one of the most fundamental things we identified was that the sorts of tools that the construction industry has to work with, namely SAP for housing and SBEM for non-domestic, are currently at best giving misleading advice, if not giving incorrect advice on the benefits of different options and the value of different strategies for saving carbon and energy, and they need to be reformed. There's nothing wrong with a lot of the underlying physics. Some of the assumptions and the reference information within them causes problems and can send people down the wrong pathway. I know this is an established fact, but even the proposed changes to those tools in the most recent versions that are not used within building standards but have been published recently still actually only go a small way towards correcting some of those issues. And I'll come on to a bit more about that in a moment. So that's the headlines, I suppose. There's a massive opportunity here. We can make a massive change. There's things to be done. They're all very doable, but we need to do it in a measured way. I won't go too much into these points in any great detail because they're really a lot of things that Lynn's already covered. I think the key thing to say about it is that there is a recognition that the ambition needs to change. We've got the same building standards now we've had for 6 years, and that's given the scale of expectation, that's really pretty poor, and it needs to change. It is being reviewed this year. The Committee on Climate Change have been asked not only to look at achieving what would be required to meet our Climate Change Act obligations, 80% reduction on 1990 by 2050, they've also been asked, is it possible and by when can we achieve a net zero UK? And that's really important in the context of whether these standards may change, because it means that the amount of investment that would be expected from a public policy perspective, what's the value of carbon? If you're trying to get to zero, that carbon price is higher than if you're trying to get to an 80% reduction. So it means that you can afford to spend a bit more to save that carbon if your ambition is higher and you're trying to do it more quickly. And because of the recent publication of the IPCC report on saying we need to be targeting 1.5 degrees, the government has asked the committee to look at what would the UK need to do to achieve that. So if they start to move to that sort of target, then again the level of investment required to reduce carbon would be higher, and the affordability of options would increase. I've mentioned the Hackett review, Lynn mentioned the Hackett review. I think it's key to say that obviously that's not addressing energy specifically, but there's a huge amount of carryover in terms of the issues that were identified, which are obviously less serious when they're applied to energy, but the same issues apply. The regulation is not fit for purpose, and be it in the form of the structure of the regulation or the way in which it's enforced. So the study that we undertook looked at a range of points, starting with what are the key considerations to inform regulatory requirements. When does low carbon heat become cost effective? And we looked at different forms of low carbon heat. What's the role of energy efficiency in the mix? And what are the costs? What's the cost effectiveness from a public social perspective? Is this value for money for the UK to set these as standards that people should be obligated to achieve? And also then, are the tools that we use to try and achieve those standards suitable? I won't go through the analysis. Effectively, we looked at a range of different building types. We assessed a whole range of different specifications and solutions by which you might achieve higher standards, focusing specifically on fabric efficiencies and low carbon heating. And then we went on to look at the capital and life cycle costs, the carbon savings, the energy savings, and the cost effectiveness, the impact on household bills, the impact on lifetime carbon emissions, lifetime energy use. So it was a similar sort of analysis that you might do for an impact assessment for building regulations, but looking at achieving very high standards of carbon reduction. We assessed both domestic and non-domestic buildings, but I'm going to talk about the domestic side of things today. A range of different house types, and we looked at the current building regulation standards and then reducing space heating demand down in 5 kilowatt hour per year per metre squared per year increments down to 15 kilowatt hours per metre squared per year, which many of you will know is broadly equivalent to a sort of a passive house level of performance. So saying that if passive house level of fabric is one extreme, and we're currently at the Partel notional standard, where should we go in between those points, or should we be looking to get to the passive house standards, and if so, how would we go about doing that? And then we combined those with the standard that's being used currently, so a gas boiler. We looked at using air source heat pumps and low carbon heat networks. We explicitly didn't look at on-site renewables, so photovoltaics. for some of the reasons that Lynn mentioned, in the sense that you can't necessarily offset your heat energy consumption. If you're using gas, you can't offset that with using PV, particularly as the carbon intensity of the grid is reducing over time. The amount of carbon you're offsetting through generating on site is reducing as the grid decarbonizes, but your gas is staying the same. So your carbon emissions effectively your net carbon emissions go up over time. So we didn't look explicitly at PV. So that's a sort of a quick overview of what we did, some of the key findings that we identified. So no surprises here, but form factor was a key variable here, and it's something that the current approach that we have of having a notional building which sets you a target that is based on the design of building that you're proposing to build is a big limitation. So if you wanted to achieve an absolute performance standard, it's much easier to do that if you're building a block of flats or a terrace of houses than it is if you're building a detached house. The fact that effectively the regulations give you an easier target if you're building a detached house than if you're building a flat is an issue when you're looking at the suitability of going to very low carbon heat solutions, where a lot of the benefits that you might get from having reduced energy demand and reduced peak demand for energy are only applicable when you get to an absolute level of space heating, which you can't do if you're using a notional building standard. So one of the key things we identified was that the notional building standard is a problem in trying to achieve better performance. We also identified the role of mechanical ventilation with heat recovery. If you want to get to the higher standards, it's very difficult to do that while sticking with natural ventilation methods. Now, we recognise there are some technical challenges with MVHR as a solution, but that it is an important part of the mix of getting to these higher levels of performance, and if it's installed correctly and managed appropriately, can be used and is an effective technology. But this is where I come back to the issue of transition, managing the change in the way in which we build, so that we can't just suddenly start building 300,000 homes with MVHR units in them. We need to be able to ensure that we can do that in a high quality way, and that the homeowners actually understand the systems that they have and can manage and use them effectively. That said, where you do use MVHR, it's really important that you complement that with incredibly high levels of air tightness, so down to say 1 meters cubed per meter squared per hour. And sorry, apologies, I'm sure you can't read this graph, but what we did was a little bit of sensitivity analysis to look at, if you have an MVHR system, what's the relationship between air tightness and the U values that you need in your external walls in order to achieve the same level of space heating demand. So if you wanted to achieve 15 kilowatt hours per meter squared per year, if you have an air tightness level of 2 meters cubed per meter squared per hour, then you need to have an external wall in your semi-detached house of 0.16, the U value. If you can get that air tightness right the way down to 1, your external wall U value goes up to 0.22, which is actually above the Part L notional specification. So if you go to MVHR and you really, really tighten up the air tightness, that gives you a lot of flexibility with the fabric specification that you use. So this expectation that in order to achieve passive house you need to be having 3 foot thick walls is naturally not the case. It's about coming up with a really good form factor and having really prioritizing the right parts of the construction. And we spoke to a lot of passive house architects and developers, and they told us how they go about achieving these high levels of air tightness. And it isn't rocket science, it isn't massively expensive, it requires attention to detail, it requires traditional technologies like using a wet plaster finish on your external walls, taking that down to the level of screed, to the level of the concrete base before you put your screed in, and lots of simple solutions that need to be rolled out across the industry, which will really massively improve air tightness, but aren't necessarily expensive to do. Yeah. Okay. So we identified some big opportunities, and not least of those was that when you achieve these very high levels of air tightness, you can start to make savings in the way in which you build your home. So you can reduce the amount of your wet heating system, reduce the number of radiators, reduce the runs of your pipework within the home, and that starts to actually claw back a lot of those additional costs. So your net additional cost comes down as you get to very high levels of energy efficiency. So what that told us, and these charts just give a breakdown of some of the additional costs, that to get to this, for a semi-detached house, circa 85 square meters, achieving a passive house level of performance, the net additional cost is under £3,000 if you do it efficiently and in a volume manner. But in part, that's achieved by saving nearly £2,000 off of that capital cost by really scaling back your heating system and getting those savings. And there's potential to go further. You might even say, well, why do we need a wet heating system? Let's go for panel heaters. Now, we didn't look at that in detail, but that might be something that becomes an option in the future if you get very, very low space heating demand. Certainly, we found that cost of that higher level of energy efficiency wasn't as high as we had expected and we had looked at previously. You then combine that with a low carbon heat source and you're looking at under £5,000 additional cost, and which is in some cases, and that's for a semi-detached house. For flats it's far less than that, it's around 1% additional cost, which given the variability of construction cost is something that gets lost in the noise, to be perfectly honest. So in terms of costs, we identified that the costs were probably lower than we had originally thought they would be. Looking at carbon, and this is where it comes back to the tools that we use to assess carbon. So this chart at the top here shows both BEIS's and the Committee on Climate Change's projections for future carbon intensity of electricity, and the two dotted lines, the top one is the SAP 2012 figure for what we use currently to assess the performance of electricity use in the home, and then the blue line is the SAP 10 figure. You can see that, okay, currently SAP 10 is about between the BEIS and Committee on Climate Change assumptions on carbon emissions. But if you look at the lifetime of that home, and this only runs to 2050, it's massively overstating the carbon impact of that electricity use. So if you're able to switch to an electrical form of heating and hot water over the life of that home, you're really creating a big opportunity for carbon saving. And it's not just in 2050, it's actually, by 2030, the SAP 10 prediction is double what government and the Committee on Climate Change expect the grid carbon intensity to be. So we're really overstating the carbon impact of electricity. And if you look at that, when you compare different house types, different specifications, you can see here, the first column there is for a gas home, makes very little difference, doesn't really change things that much in terms of the performance. If you look at the heat pump options, you can see that going from the blue column, which is our SAP 12 figure, through to the future whole life carbon impact based on the future carbon projections, actually the difference between, say, just over 14 kilos of carbon per metre squared to under 2 kilos of carbon per metre squared, it's night and day. So the tools we're using are not giving us good information about the whole life impact. Right, I'll be quick, sorry. This analysis as well, which was looking at, if you cumulatively assess what's the carbon impact of using a traditional gas boiler at the Part L notional specification, keeping a gas boiler and building close to a passive house standard, compared to using an air source heat pump and the notional specification, and an air source heat pump and the and the passive house standard, told us some really interesting things. So the blue line there is the cumulative carbon emissions of a home with a gas boiler built to Part L. If you were to build that to a passive house style spec, that light blue line will show that you're saving about 40% of the carbon emissions over 60 years. However, if you were to use an air source heat pump from day one and still build to the Part L specification, so no energy efficiency, your actual carbon savings over 60 years is 90%, is over 90%, so far higher than the energy efficiency. Just shows the importance of getting to low carbon heat, and importantly hot water rather than necessarily the heat. And if you were to go to a passive house spec, you actually save only maybe a couple of percent more in terms of the overall carbon savings over 60 years, because the electricity is so low carbon for most of the life of the home. Doesn't mean you shouldn't do it, but it just shows there's very little additional carbon benefit from going to a passive house spec over a Part L notional spec. But if you were to start off with a gas boiler and then retrofit in an air source heat pump 10 years into the life of the home, which is really too early, but nonetheless, let's say you did it after 10 years, your lifetime carbon emissions would be 3 times higher than if you started with an air source heat pump from day one. So even that 10-year wait to install a heat pump really has a big impact on the relative whole life carbon impact of the home. So it's important that we make this transition quickly and don't delay, because if we're building large numbers of homes quickly over the next decade, we need to ensure that as many of them as possible have low carbon heat. I will stop now. All I was going to say very quickly was it's really, I mentioned that the carbon benefit from building to a passive house standard is small, but our recommendation is it should be done nonetheless, because you save significant utility bills, and also it has a big impact on reducing the peak demand for energy, and therefore the wider energy system can operate much more efficiently if you have a very energy efficient home which can trickle heat throughout the day, rather than having peaks in demand at certain times of the day, which will put unnecessary additional strain and cost on the infrastructure. Okay, thanks.